First talk is given by Jen Heldmann, use of handheld field instruments to enable lunar polar volatile studies by Artemis astronauts. Please take it away, Jen.
And I think thanks for putting me in the session that starts with problems. That's always fun. So hopefully we can spark some discussion in the Q&A and then for later today. We'll talk about handheld instruments to enable lunar polar volatile studies by astronauts. And I want to acknowledge contributions from Julie Mitchell, who is formerly of the NASA Johnson Space Center, and Tony Colaprete at NASA Ames, and a whole cadre of folks who have been working on this problem for many years now. We could go to the next slide, please. I want to start out, this is a little discussion that was happening earlier today in the meeting about astronaut capabilities, and there was some chat in this, or in the chat box. So I wanted to point out what's in the Decadal survey. This is the National Academy's Decadal survey for planetary science and astrobiology, which was recently released. I co-chaired the Human Exploration Working Group with John Grunsfeld. And in this chapter, we wanted to make a point to highlight how and where human expertise is most valuable for addressing high priority science questions. So I won't read this chart here, it's table 19.1 in the report. But what we did is made a conscious effort to map human expertise, that's in the left-hand column, to science objectives. And the first objective listed is determine the origin, composition, and history of ice deposits on the moon and Mars. And then the science questions that are relevant for that. One of the findings, and this has been harped on over and over in this meeting today, is that sustained human exploration, the astronauts need to have appropriate training and mission planning. So this is a finding in the Decadal survey report. We want to make sure that that was there. And that's how we will conduct and enable the highest quality Decadal level planetary science. And so in order to do this, NASA should engage with the science community early to define the science goals. And two, something that's come up a lot today, ensure the scientific expertise in field geology, planetary science, astrobiology, et cetera, in its astronaut teams. So I just want to emphasize that point. Next slide, please. We're talking about volatiles here, just to get us all on the same page. What are we talking about in this presentation? So if you look on the left, this is a graphic that we also had in the Decadal survey. I led a mission concept study about a long-range rover to study lunar polar volatiles. And this is a great graphic that James Keene made showing the temperatures, the sublimation points for different substances on the lunar surface and other planetary bodies as well. So as you can see, as you get colder, you sequester more volatiles. And the thermal regime is really important here. It's the temperature that dictates which volatiles will be cold trapped over geologic timescales. So the colder the temperature you have, the more volatiles you have the potential to trap, and that will give you a more complete record of volatile histories. You can see on the bottom image, I love this image, it's in the Artemis 3 SDT report and the Decadal survey report, that volatiles or hydrogen abundances are spread out. This is the lunar south polar region. We don't understand the distribution, why some craters and not other craters, why some areas and not other areas. So these are some of the science questions we're trying to address. Next slide, please. Sam Lawrence gave a great overview already, so I won't harp on this, but of the Artemis 3 Science Definition Team report. In their report, lunar polar volatiles come up a lot as a high priority science objective for Artemis. There are 6 specific goals there. I won't read them, but you can look at the report yourself. You can distill it down to essentially trying to understand the age, the origin, and the evolution of volatiles. We use the moon as a witness plate, which records the geologic history of the inner solar system of volatile activity. A lot of that history has been erased on other bodies, but the moon is the most accessible place where we can go and understand this story. Next slide, please. So when we're talking about Artemis astronauts, I want to talk about a few different ways we can collect measurements. So first we'll start with in-situ measurements and why these are so important. So what we would do with in-situ measurements. By doing this, we minimize sample alterations. We don't want to change the composition, the stratigraphy of any ices that are found. 2, we want to increase the fidelity of the science measurements. And 3, serve as a ground truth for sample analyses. There will be some alteration when we bring those samples back. We can ground truth them in situ. And 4, facilitate successful sample return in terms of understanding contamination monitoring and have a baseline measurement for sample composition. The astronaut suits will leak. Gases will come out of the suits. So we can measure this and we can quantify it so we can better interpret the data that comes back from sample return. There was some discussion in the chat earlier about temperatures. How cold do you need to have your samples? Do you need to have them cold? Ideally for science, yes. We would like to have volatiles returned at cold or cryogenic temperatures. Ideally, you would like those samples to not get warmed up above the temperatures at which they naturally occur. And here's why. As you increase the temperature for your sample return, you increase your sample alteration. You're going to have phase changes. You're going to have chemical reactions occurring. You're going to have pressure increases in the sample container. And ultimately, you'll have a loss of science. So if the temperature goes up above that sublimation temperature, those volatiles will change from a solid form into a gaseous form. Those gases can be contained in the headspace of your sample return container, but it can be very difficult to figure out the original state. And here's just one example, a chemical reaction if you consider methanol. You can see the potential reaction chain. You can see the changes that happen from the original state to where you might end up. And this is just one species. If you have multiple species coming, into the headspace, into the gaseous form, those species are also going to interact, and it quickly becomes very complicated, and it's very hard to retrofit, figure out what was originally there. So if we can keep those samples at colder temperatures, it's much better for science. Next slide, please. And just there was chat before, yes, the space-rated freezers now are at about -80 C. That's what's needed for biological samples on ISS, for example. When we're looking at, lunar polar regions, I'll show you some plots where L-cross impacted was 40 Kelvin, right? That's much, much colder. When you see on the volatiles plot, you're talking about tens of Kelvin to 100 Kelvin, maybe 200 K. Those are the temperatures where we're looking at volatiles. So it's a bit colder than what we have the capability for now. Okay, how will we measure volatiles? Okay, so in thinking about, what is the instrumentation that we need to do this? How would we look for composition? Well, we do have one ground truth measurement. That's the L-CROSS mission, the Lunar Crater Observation and Sensing Satellite, impacted Cabeus Crater at the lunar South Pole in 2009, and measured a whole slew of volatiles. So here are plots. This is from Tony Colacrete's science paper in 2010. A lot of volatiles. You can see all the different species there. So we know that this wavelength range is good for measuring these lunar volatiles and could be applicable to handheld instruments. Next slide, please. We're also sending another mission to look for and map out lunar polar volatiles. And this is the VIPER mission, the Volatiles Investigating Polar Exploration Rover. It is specifically designed to measure the composition of lunar polar volatiles. So on VIPER, we're flying two instruments for composition. One is NIRVIS, the Near Infrared Visible Spectrometer System. Wavelength range, we can see the wavelength range there, specifically tailored to look for volatiles. And also M-SOLO on the mass spectrometer. NIRVIS comes out of NASA Ames, M-SOLO comes out of NASA Kennedy. M-SOLO measures constituents below atomic number 100, focusing on the volatiles that are of interest. So we do know what instruments and the specific capabilities that are needed for looking for volatiles because we have sent robotic missions to do this. So these are the types of measurements that would be useful for Artemis astronauts to make as well. Next slide, please. So I want to talk about non-contact measurements first. The rationale, if you have a non-contact measurement capability, this is useful because you will minimize the activities near that measurement site and limit the impacts to the environment and the volatiles themselves. So you have the minimum amount of disruption. So in order to do that, there's work going on in multiple groups. I will just show this as one example. A field portable version of VIPER's NIRVIS instrument. We know NIRVIS is covering wavelength range with the sensitivities that we need. So there's a backpack version that's been tested out in the field. You could imagine astronauts taking something like this and making these measurements as well. Next slide, please. There's also contact measurements that can be made in situ. You want to measure subsurface compositions and stratigraphy with minimal disruption to the natural state of the volatiles, of course. There are a few ways that you could actually do this. You can trench. There's discussion about how to trench or build a wall and using handheld instruments to image and collect compositional data. You can drill, bring that material to the surface for imaging and collect your compositional data that way. You can drill a core, and then you can bring that core up and scan that with your handheld instruments. You can have integrated instrumentation in a drill string for downhole measurements. So there's development work going on each of these fronts. On the bottom, here's some handheld instruments. Erica talked about these instruments before. Oz has talked about these. If you have to ruggedize them for use on the moon, but if these are what are producing the valuable measurements that are needed, then we need to consider them for ConOps for astronauts. In terms of the next generation of drills, so there was discussion earlier about what kind of drills you need to go through ice. So Viper is using a rotary percussive drill, and that will also be flying on the Prime 1 mission. So there are 2 missions going to the lunar South Pole that will be drilling. And the next generation of this is drill integrated instrumentation. So through the Survey project, through the resource team, and in collaboration with Honeybee Robotics, we're actually doing this now and developing the drill integrated instrument system. So this is taking the Trident drill and integrating a neutron spectrometer, the near-infrared visible spectrometer, a thermal sensor, heat probe in the drill string, so that when you drill down, you're bringing the instruments to the sample, as opposed to how Prime 1 and Viper will work, which is you drill down, bring your sample up to the surface, and then look at it there. So next generation of drill work is going on now, which I think could be very, very valuable. Next slide, please. How to measure volatiles. So how do you figure out what the physical form is? Because this gets back to a lot of science questions that are outlined in the Artemis 3 STT. There are a multitude of different physical textures that are possible to lunarize. We don't know what we will find yet. I love this image that Kevin Cannon has produced from Colorado School of Mines of all the different ways ice and dirt and rock could be mixed together. You can use imagery at both the micro and macro scales to get to these questions. You can also use the drill itself on looking at subsurface strength, so drill power, weight on bit, etc. You can constrain the subsurface characteristics. Viper will be doing this and getting to some of the geophysical properties of the surface and the subsurface. Next slide. Thermal measurements as well, just to reiterate, it's the thermal regime which drives which volatiles are able to be sequestered in different regions. This is going to get to the ice stability and the ice history, and I'll remind you of this chart so you can look at the temperatures that we're talking about. For L-Cross, we detected H2S. That's, tens of Kelvin, right? It's very, very cold. And as you get warmer than that, you're going to start losing those volatiles. So this is very different. This is, I think, one of the biggest differences from operating in Apollo is we have these very cold temperature regimes that we're ultimately going to be working under. Next slide. Okay, so utility of astronaut field work. So humans are uniquely able to contribute to volatile science at the moon. And John Grunsfeld has given a really great talk just last week about the capabilities of humans and how humans can uniquely conduct science on planetary surfaces. So you can find that talk, that would be great. We can enable key science measurements. We provide information for selecting sample sites and high grading samples for Earth return. We've talked a lot about this today as well. And in terms of volatiles, volatiles are special because we'll also be informing in-situ resource utilization or ISRU architectures with this ground truth data of volatile deposits. So there's both a science and an exploration aspect to doing this work, which is beneficial to multiple groups across the agency. Next slide, please. Okay, so what do we need to do now in order to make this happen? So this is a table that I also pulled out of the Decadal survey report. And these are representative Science Mission Directorate research and development activities that we need to do to enable and optimize high priority science from Artemis. So hopefully this can be useful to SMD, pointing to the Decadal survey saying, look, this is all the work we have to do. This is why we're funding these activities. Some of this is going on now, some of it's ramping up. But relevant to volatiles, cold sampling and curation, it's very difficult and we don't exactly know how to do this yet. Sample science, which we talked about today. In-situ measurements, we talked about for volatiles, for impacts, for volcanics, all sorts of planetary science. Getting the science requirements down, which are needed in order to drive the human architectures to make sure we have the science capabilities that we need. Landing sites, science accommodation trades. If we're mass limited, do you bring handheld instruments? Do you want to trade that against deployable instruments, against your sample containers, your sample return? There's a lot of trades that need to go on. Imaging and situational awareness, science, concept operations, and of course, crew training. So these are all the activities that we need to do to make this work. And I think I'm right on time because that is my last slide. If you go to the end, yeah, I think that's it. And I'm happy to take questions during the Q&A.